Professor Liu Zouwei. Yeah? Oh. Okay. It's about atomic dark matter. Okay. First, I want to thank the organizers for inviting me to talk here. So I'm going to tell you about the atomic dark matter. So this is the outline. So I will first talk about what is atomic dark matter. The model we consider is a miniature atomic dark matter. And then the direct detection signal, since the laser is feeling way. So then I will tell you about the scattering of atomic dark matter and in the context small scale puzzles. At the end, I will discuss some recent anomalies in the indirect detection signal 3.5 keV X-ray. So these are the papers I had with my collaborators. So I will, there's some literature in atomic dark matter models. I will, in this talk, I will mainly focus on my papers and our contributions. So this is the setup of the model. So just like in the visual sector, we have a hydrogen atom which are bound state of two fermions, one electron or one proton. So the binding force is the EM field, the photon. So we can introduce similar field content in the hidden sector. So we also have two fermions, one we call it the dark electron, the other one dark proton. And so they also form bound state in the early universe as atomic states. So this is the topic of my talk. So we further introduce the epsilon parameter between the two sectors, just like many people in this room do. The connecting mixing term between the two U1 field. So the terms here between the photon and the dark photon. So without this epsilon, there is no interaction between these two sectors. Okay, so the canonical procedure for removing this kinetic mixing term is to do a field definition. So here we choose, because there are two massless modes in this interaction Lagrangian, so we have freedom to choose one of these, freedom to choose the field definitions. So here we choose a asymmetric rotation, showing here. Under this rotation, the interaction between the two gauge field and the currents in the two sectors is given in this interaction Lagrangian. So the first gauge boson A prime is the dark photon in the hidden sector, which does not couple to the standard model currents under this field definition. So the other gauge field is the SM photon, which couple to both sector. Now, in the coupling to the standard model currents is the standard EM coupling E. To the coupling to the hidden sector, the strength is suppressed by the small parameter epsilon. So, in the literature, this is usually called the Milli charge of the hidden fermion. So the size of this Milli charge is similar to the connecting mixing term epsilon tilde in the original interaction Lagrangian. Okay, so the shape of the atomic dark matter depends on the mass ratios of the two fermions. So if the mass of one fermion is much larger than the other one, so the atomic state looks like a lot like our hydrogen atom. If the two fermions have similar mass, so the orbiting around each other, so the atomic dark matter looks like the positronium. Now, unlike the SM positronium, because the two fermions are different, this atomic state also stable. So we just borrowed the name dark electron diproton. In our model, both fermions are elementary. Okay, so in the early universe, just like our hydrogen atom, the dark atom has to recombine to form in the early universe. So we assume there are some asymmetry in the hidden sector, just like the baryon symmetry in the standard model sector. So this symmetry in the hidden sector generates the rate abundance of the dark electron and dark proton, which recombine to form a dark atom. There are calculations by Kaplan group. So they compute this recombination in the early universe. So the result can be approximated by this formula. So this Xe prime is the ionization fraction of one of the fermion. So if we are interested in the atomic dark matter, so in the parameter space, we have to suppress this ionization fraction. So this has to be much smaller to have the atomic component as the dominant component in the universe. Take both fermion mass to be GeV. You can see the alpha prime, which is the coupling strength in the hidden sector, cannot be smaller, much smaller than 0.01. So this is understood because for much smaller H coupling, the atomic state cannot be formed efficiently in the early universe. Okay, so next I will discuss how to directly detect this dark matter. So for the case one the fermion is much heavier than the other one, we write the charge currents, charge density of the atomic atom as follows. So there's delta function from the dark proton, and there's a wave function. So the contribution for the dark electron. And in the low wave number approximation, we can compute this Fourier transform, and in the Born approximation, we can compute the cross-section, which is shown here. So these are the cross-section of dark matter with our proton. Now this A0 prime is the Bohr radius of this new atom, and mu is the reduced mass of the dark matter and the proton. Epsilon is the overall epsilon. So the cross-section proportional epsilon square. Epsilon is the meter charge. So turning off epsilon, the meter charge, there's no direct detection signal. Okay, so here is the direct charge signal coming from this dark matter. So here x-axis is the mass of dark matter, y-axis is the coupling strength at the meter charge epsilon in the here. So the first two lines, the first line is denoted as CMB. So here we demand the decoupling between dark matter with CMP in order to avoid the damping to the dark component. So the red line is the absorption. So because the dark matter direct detection experiments usually takes place in the underground lab, so we have to compute the absorption effects due to the rocks above the underground lab. So here is the stopping effects of a 1,000 meter rock on dark ions. So in order to detect these dark ions, so the epsilon has to be smaller than this red line. So here are the two the limits from the cogent access events and also xenon 100. Here we use atomic component to feed the xenon 100 limits, and also the ion component to feed the xenon 100 signal. Okay, so the other case is the two fermions have the similar mass, so they will orbital around each other. In this case, in the leading order, because there's cancellation between the charge of these two fermions, so in the leading order or approximation, the elastic cross-section is 0. So here we consider two other interactions. One is the spin-orbital interaction, the other one is spin-spin. So in the spin-orbital interaction case, the orbital momentum is the proton, and spin is the fermion in the dark hidden sector. Otherwise, if we switch, the interaction will be spin dependent, suppressed. So here the direct detection signal in underground dark matter experiments. So there are two terms. One is caused by spin orbital interaction given here. The other one is the spin-spin interaction. Usually spin dependent signal is the limit is the signal is small. But in this case, the spin dependent cross-section can be also sizable. Okay, so here is the diagram showing the process in the direct detection experiments. So we have a dark atom which interact with the normal proton or T-channel or photon. Now the coupling between the photon and the dark atom is suppressed by the mealy charge epsilon in this vortex. Now in ours, in the degenerate case, we assume the dark atom in the ground state, which is a spin singlet state, and through this interaction in underground lab, the spin singlet dark atom can transit to a spin triplet state. So this is similar to the hydrogen atom transition, the high profile transition, which is the 21 centimeter transition. So so here we compute the high profile splitting, and in this model is equal to this number. So here are some properties of our atomic dark matter. It interacts with our proton or magnetic interaction, and it is still isospin violation. So as you can see, there's a mass gap between the dark matter and the spin triplet stage. So it's an inelastic scattering, and it also has a non-trivial velocity form factor, as shown here. So the velocity form factor is not a standard. Okay, so our original motivation was try to feed the cogent access. So here are the parameters we feed the cogent access. So this is energy spectral cogent, and this is modulation signal seen by cogent originally in 2010. So our model parameter, the dark matter 10 GeV with the inelastic mass gap about 25 keV, and epsilon is 0.03, which is quite large. So our cogent access is no longer promising, so the coupling should be smaller. So we have analyzed more recent direct detection constraints on this model. So here is the x-axis is the mass, y-axis is the meter charge. The region where we can feed cogent is right here, and these are the limits from LUX, CDMS light, and super CDMS. This is the analysis done 2014. There are more recent experiments from Gina Wan Tang and Panax, so the limit is more stronger now. Okay, let me move to the second part of my talk. I want to discuss the small-scale puzzles and the self-interaction with dark atom. So as many of you may already know, the lambda CDF is very successful, but in small scale it faces three problems. So this is known as small scale puzzles. So the first one is called cusp and core problem. In the in-body simulation, the density profile is predicted at the cusp shape, but the observation favors the core structure in the center of the halo. And the other one is a missing satellite problem, where there are less satellite observed in the Milky Way than the simulation. The last one is too big to fail. It means the predict central density in the satellite galaxies is much higher than what we see in the observation. So in 1999, Spergel and Stanhart proposed a solution to this problem. If the dark matter can self-interact with the self-interaction divided by the dark matter mass as 1 bar per GeV, all these problems can be alleviated. Okay, so in our model, the dark atom is a composite state. As we know, composite object has a larger scattering cross-section, so we think this might be an excellent candidate to solve this problem. So we compute the self-interaction cross-section of this atomic dark matter. So to compute the self-interaction, we solve the Schrödinger equation for the radial wave function R. So this is just quantum physics textbook calculation. So the problem here is we have to find what's the potential between these two atomic states. Okay, so the problem has our model has three parameters. One is alpha prime, which is the gauge coupling in the hidden sector, and the two masses are two fermions. We can translate these three parameters to alpha prime, the dark matter mass, and the last one is the ratio of these two fermionic components. So R. So please remember this R definition. So we'll enter this Schrödinger equation in the next slide. So here is just the standard treatment of this Schrödinger equation. So we work in atomic state units. So in atomic units, the distance is in units of Bohr radius, and the energy is in the unit of twice of the binding energy of atomic dark matter. So in atomic units, the Schrödinger equation is simplified as the shown here. So all the new physics parameters enter in one place, which is in front of this energy and the interaction potential. So, and this parameter is very simple if we ignore the binding energy of these atomic states. So this is the Schrödinger equation. Without binding energy, F is just proportional to R. So R is the ratio of the two fermions, so it's bigger than 1 by definition. So as you can see, we can go much larger R, so this F just go as R. So R just acting a particle mass. So we solve this Schrödinger equation with the particle mass proportional to R. Okay, so the interaction potential V depends on the spin configurations of these two atomic states. So so for spin singlet and spin triplet configurations, the interaction potential are different. So we took the interaction potential from atomic physics literature. So the potential is given here. So the x-axis is the distance in atomic units. The y-axis is the potential also in atomic units. So in our problem, because this is in atomic units, so we can just take this potential and use in our Schrödinger equation. We solve this scattering cross section. Okay, so so we use a partial wave method to solve this scattering, and because the overall wave function should be symmetric if we change the electron and the electrons and the proton at the same time. So the partial wave cross section should be modified to take into account these effects. Now, for the even orbital momentum, the spin state has to be also symmetric. So the spin state should be spin singlet times in electron and the spin singlet in proton. And also spin triplet in dark electron and spin triplet in dark proton. So this is symmetric in exchange of two spins, and this is also symmetric in exchange of two spins. So orbital part also symmetric. In the antisymmetric case, the orbital part, both the orbital and the spin part has to be antisymmetric. Okay, so we use this calculation using the partial wave to this formula to calculate the self-interaction cross section, and this is the result. The y-axis is the scattering length. The x-axis is the R value, which is acting like effective mass. So as you can see, there's many resonance as expected in the scattering calculation. So the triplet is much weaker and only have one resonance, and the singlet potential is much stronger, so it has many resonances. So we check our real world, the value R is 1036. So it turns out our real world is very close to one of the zero. So our atomic cross section is much smaller than the typical values, which is in atomic units. So is here our real world is only 25. Typical value is in the range of 100 to 2,000. So we try to reproduce the known results in the atomic literature. So here the calculation, the x-axis is the energy in unit atomic units, and the y-axis is the cross-section divided by A0, the Bohr radius square, so also atomic units. So here are the different L value we used, the partial weave. So as you can see, below energy 0.01 in atomic units, we need to go to L as 40 to produce the limits. Okay. So here we change the R values also for different L mode. You can see we can produce many different resonance in this scattering and energy plots. So this looks like we can fit many. There's a requirement on the cross section. We can fit this easily if we're sitting on the resonance. Okay, so in order to accurately calculate these effects in the small scale structure, we have to compute the transport cross section instead of the elastic cross section. So the transport cross section is given by this integral. So it's the cross section times 1 minus cosine theta. Now in our case, because the dark matter are identical particle, so the forward direction and the backward direction are the same. So we have to treat the forward, the backward scattering as the equivalent. So we modify this transport cross section as here. So at the forward and backward direction, this cross section gives the same value. And in terms of the partial waves, of course, the calculation given here. And this comparison between the transport cross section and the elastic cross section, and the x-axis is the energy, y-axis is the cross section. As you can see below 10 to minus 2, the two cross sections are basically the same. So as we go to higher energy, the transport cross section deviates a lot from the elastic cross section. So here we further feed these transport cross section with some analytic feeding function. A0 plus A1 energy plus A2 energy squared power minus 1. So here the fitting result. Okay. So so we feed the transport cross section in this simple formula. In our fitting, we find this A0 is roughly 0.01. So in the low energy, the transport cross section is roughly 1 over A0. So in atomic is about 100. So we will use this in so as an estimate of this atomic scattering cross section. So now back to the requirement on the small scale puzzles. We have to have this cross section over dark matter mass as 1 bar per GeV, which is roughly 0.6 centimeters squared per gram. So we consider different systems for dwarf galaxy or Milky Way-like galaxy and galactic clusters. So these two systems have different velocity dispersions. For dwarf galaxy, the velocity is roughly order 10. And for Milky Way galaxy, the velocity is about 100, and galactic clusters about 1,000. So for these different velocities, we require the interaction cross section or the dark matter mass to produce the 1 bar per GeV value. So here are the result. The x-axis is the R value, the y-axis is the cross section, and we choose different alpha value in the hidden sector, and the lines is where in the parameter space we can get this self-interaction cross section. Okay, so in the remaining several minutes, I will discuss to the 3.5 keV X-ray line anomaly in our we use our model to explain this anomaly. So this anomaly was observed by several groups in 2014, and so there are also recent observations. So following this study, there's also recent observations of this 3.5 keV. So in our model, we use the hyperfine splitting to produce this this 3.5 keV line. So the energy gap between the here is just like a usual hydrogen atom in our sector. So the ground state is a spin singlet, and the first excited state is spin triplet. So the energy gap between these states we set to be 3.5 keV. Now we consider two scenarios in our model. One is the slow, inelastic scattering, which excite the ground state dark matter to the first excitation state. Then there's fast decay of this spin triplet state to emit the 3.5 keV line. And the other scenario is the fast scattering, which excite the ground state to the excited state, and the decay of the excited state is very slow. So the universe will be formed by these three to one spin states of this atomic dark matter. Okay, so I will emphasize the signal is always determined by the slower process. Now for the fast decay scenario, the fast decay of the excited states, the signal requires the excitation, the self-interaction cross-section times the Bragg ratio in this value to produce the signal strength. And we assume the spin excitation cross-section is roughly the same as the elastic cross-section in the self-interaction. So which takes a value of 100 atomic units. Now for massive dark photons, the Bragg ratio is the ratio between the coupling to the visible sector epsilon square alpha divided by alpha prime. Now for massively dark photon case, this requirement will either require a much bigger epsilon value and or a bigger self-interaction cross-section. So it turns out the massive case is excluded by experiments. So we have to consider a massive dark photon. In the massive dark photon case, the mass is the dark photon mass is heavier than 3.5 keV. So we have the Bragg ratio as 100%, and the cross section. All these decays of the excited states will emits standard model photon. Okay, so for the massive dark photon case, we have to introduce additional Stickelberg mixings. Otherwise, the meter charge will go to zero with the only connecting mixing. So, here the discussion on the two different mixings and the media charge. So let me speed up. So for the massive case, we calculate this signal strength and also the requirement on the mass gap. We combine these constraints. The mass is predicted as a function of FR only. And for the media charge, the constraints from direct detection experiments, so we compute the epsilon must be smaller than roughly 10 to minus 7. So these are the limits about 3 years ago, so now it's more stronger. Okay, let me skip this one. So these are the constraints summarized on this plot. The x-axis is the mass, the y-axis is the media charge. So the red lines are the constraints from lux for different R values. And these are the constraints to in this scenario. And the line here is the favored parameter space to produce this 3.5 signal. And these are just the mass case where the epsilon is too large, has to be ruled out. Okay, so I think I'm running out of time. So these are the summary. So thank you.
Any question? Okay. So it is scenario consistent with the cosmological structure formation scenario. Since you have the charge, there may be the extra process for the structure formation process.
Sorry, can you say it?
So I can put it another way. When is the coupling time for the dark matter?
So the decoupling time of the dark matter with the
So
mass.
you have the proton, dark proton, and dark electron, which should be in a plasma state in the early universe. So when is the recombination time?
Oh, okay. It depends on the coupling and also the mass. So I don't have the calculation showing the recombination time, but it could be different from our recombination time.
If the coupling time close to the coupling time of the user matter, then this dark matter affects the structure formation process. Did you check that?
I didn't work on that aspect, but there's some other papers in the research. Okay. Sorry, I don't have an answer for that.
Okay, thank you.
Okay. Okay, wow. Okay. This be a quick question.
So just to clarify, okay, so media charge usually refers to dark photon as massless, meaning that the dark matter carries our electric charge. That's called the media charge.
That's the same definition here.
But with Zuckerberg mass term, there's no media charge, it's zero. The dark matter does not carry our electric charge.
No, that's not true. We still will mass mixing, there will still be.
There's a very big difference between dark photon, whether dark photon is massless or not. There's a huge difference.
Go back to that slide.
Yeah. We can talk about that
So
later.
here,
Yeah.
so if the Zuckerberg coupling, the mass mixing parameter is 0, dark matter, which is here, so does not couple to our photon. So this is the meter charge, which is the charge of the hidden sector fermion with respect to our photon.
When the Zuckerberg mass is 0.
Zuckerberg
I don't-
coupling.